Today, we will speak about rotating black holes. On the blackboard, you can see the Kerr-Newman solution, which was found in 1965, and which contains a number of parameters. The first rotating black hole was found in 1961 by Kerr, and it has immediately improved our understanding of the gravitational features of black holes. So today we will speak in detail about its properties, the horizon, and the singularity. So, first of all, the Kerr-Newman solution is the most general asymptotically flat solution that is stationary and axisymmetric. We will touch these details in the next lectures. This will be covered by when we will discuss uniqueness theorems. So, the Kerr-Newman solution. So, as you can see, the Kerr-Newman solution is more. So, as you can see, the Kerr-Newman solutions is more complicated than the Rice and Nordstrom one. Here, we do not assume the spherical symmetry. And the solution has only two Killing vector fields. The stationary one, d over dt, and the axisymmetric, which generates the 2 pi periodic rotation, d over d phi. The solution is given the so-called Boyer-Lindquist chart. And this is the asymptotically flat chart, in the sense that at the coordinate r going to infinity, the chart approaches the Minkowski metric. So the solution is asymptotically flat, and its parameters directly correspond to the charges as measured at infinity. So this solution has 4 parameters. These are the mass, which corresponds to parameter m. This is the angular momentum per unit mass, which is the parameter a. These are the electric charge q and the magnetic charge p. So if you take the limit e equals 0, that is q and p go to 0, we will recover the Kerr limit. If we kill the rotation, that is set the angular momentum to 0, we will get the Rice and Nordstrom solution. To study the structure in more detail, I suggest limiting ourselves to the Kerr black hole. So on the blackboard, you can find the Kerr solution in Kerr coordinates. So what is the benefit of these coordinates? Well, if you could notice from the Boyer-Lindquist coordinates, if delta equals 0, the metric became degenerate, and which means singular. Here, we're doing the same thing we have done for the Schwarzschild and Rice and Nordstrom black holes, where we have introduced Eddington-Finkelstein coordinates. Here, we have introduced 2 coordinates, a new time-like coordinate v, and a new angular coordinate chi, which brings the metric into a new form. So, notice that the new angular coordinate chi is also 2 pi periodic, because it is dependent on phi, which is 2 pi periodic as well. So, for convenience, let us decompose delta into positive and negative root. So, if we can do this in a sense that if delta is always manifestly positive, then we will have a naked singularity, which is similar to Rice or Nordstrom. We'll show next that there is always a singularity, and if delta is positive, then we can reach it, and there are no horizons. So, let us assume that delta has 2 different roots. So we denote the exterior root as r plus. So here, in Kerr coordinates, the metric is regular at the roots of delta, and we can extend behind this coordinate singularity. So the roots of delta therefore correspond to horizons, and we have a similar picture to Raster Nordstrom, where we had an external horizon at r equals r plus, and an interior one at r equals r minus. We will discuss it later when we will start drawing the diagrams. So, the two killing vectors in the new chart correspond to the d over dv and d over d chi vector fields. And checking this remains an exercise. So, what are the features? We have just said that the geometry exhibits horizons at r plus and minus, and the geometry also exhibits a singularity. At sigma equals 0. Now, notice the complication, because sigma is the sum of two positive terms, which means that both of them must vanish. So sigma is no longer. So the singularity is no longer the center of the spacetime. Instead, it is a one-dimensional line, effectively a ring. Sorry, I meant that on a space-like cross-section of the spacetime, the singularity will be a ring, because of course the singularity is a ring or a point times the timeline. So sigma is 0, and therefore it is r equals 0, theta equals pi over 2. So the ring singularity exists only in the equatorial plane. Now, let us see how geometry behaves at the exterior horizon, r equals r plus. So let's consider r equals r plus. So the normal is given by dr, and raising the index, the normal vector field is given by a linear combination of both k and m. It's given by k mu plus some constant, m mu. The constant is given by checking this remains an exercise. So, is this vector null on the horizon? Well, yes, it is. Sigma squared, so that's psi on h plus, psi on h plus, and psi squared on h plus equals psi mu, which is indeed 0, because here we have radius and here we have time and angle. So the exterior horizon is as well a null hypersurface. Yeah. Now, if you think about it, something strange is happening. Before, we always had that the horizons were with respect to stationary vector field, which was a stationary vector field for the asymptotic observer, in the sense that the horizon was stationary and static with respect to the asymptotic time. Here, the normal to horizon is a combination of time lag and angular vector field. So what does it mean? Let us consider the generator of the null hypersurface, that is the null geodesic. Okay, so to see this, let us consider a null generator. So the integral curve of the psi mu. So one can see that psi mu preserves the following combination of angle and time, and therefore the integral curves can be characterized by therefore the set of integral curves therefore the set of all integral curves can be characterized by this algebraic equation. So therefore the curve is effectively rotating with the angular velocity of given by omega h. Rotating with respect to the asymptotic observer. This therefore allows us to call this black hole a rotating black hole, because we of course identify ourselves with the asymptotic observers. Now let us look at the diagrams. So it's not easy to draw the Penrose diagram for the Kerr black hole, and the reason is the lack of the spherical symmetry. But let's go step by step. We have introduced the Kerr chart, which covers the region behind the black hole, the exterior horizon. And similarly, we can introduce the second coordinate, and we can introduce the Kruskal-like coordinates, and then continue with the standard procedure. The reason is that for the spherically symmetric solutions, we could just project, while here we have dependence on theta. So this means that we'll have to draw the Penrose diagram for each theta. Fortunately, our dependence on theta comes through trigonometric functions, so it's sufficient for us to know how it behaves. So it's sufficient for us to get a qualitative picture. It's sufficient to us to see how it behaves at certain values. So let us consider the equatorial plane. The equatorial plane, given by theta equals pi over 2, is a very convenient submanifold. First of all, well, its primary feature is that it's totally geodesic, in the sense that if we have a geodesic starting at this submanifold, it will geometrically remain within it. So, within this submanifold, we can then draw the Penrose diagram. The diagram is somewhat similar to the Reissner. The diagram is somewhat similar to the Reissner-Nernstrom black hole. Notice that we have infinite copies of the space-time, because the region to the future of the interior of the black hole is isomorphic to the white hole. So we have the isomorphism between the region 3' and 3. This diagram can be extended forever. The difference is the structure of the singularities, which now instead of being the points at the center of the space-time, are just rings, and they can be avoided. So, therefore, we draw them in a dashed line. Again, we have two horizons. And we have the similar problem that the interior horizon is the Cauchy horizon. Again, we can show that the geometry exhibits an infinite blue shift at r equals r minus, and we again believe that this horizon is unphysical. This is of course the Penrose diagram for the non-extremal black hole. For extremal black holes, the geometry similarly exhibits an infinite throat, and the single horizon becomes the Cauchy horizon. We will now show how we can mine energy out of the rotating black holes. Recall that we are the asymptotic observers, and we define energy with respect to us. So with respect to asymptotically stationary killing field, which is K. As we have shown, K is not the null generator of the horizon, and in fact it is space-like there. So let us write down the norm. So K squared equals minus GTT, plus GTT, equals minus delta minus A sine squared theta over sigma equals minus 1 2mr r squared plus A squared cosine squared. So this means that for A greater than for R greater than m plus square root m squared cosine squared theta, K is time-like. And for R less than this value, it is space-like. We will call this region of the space-time to be the ergosphere, and the boundary, where K becomes null, the ergosurface. Just to put this into perspective, this is of course so we of course are interested in the exterior of the black hole. We don't want to cross the horizon, so we define the ergosphere to be the region where the asymptotic stationary killing field becomes space-like. So what is the meaning of the ergosphere? So since in this region our asymptotically stationary killing field is space-like, it means that there are no stationary observers, in the sense that the stationary curve, the radius and theta and angle equals 0 curve would necessarily be space-like. In other words, any causal geodesics within the ergosphere would rotate. Now the energy extraction. Let us consider the observer, the time-like object, sorry, and it has momentum mu equals u mu, where mu is the rest mass and u mu is the forward velocity. So we define the energy as, with respect to the stationary, asymptotically stationary field. So this is the scalar product of the stationary killing field times the momentum. Since the geometry has symmetries, has killing fields, it will necessarily have conserved charges, which can be used for the geodesic equation. So one of these conserved charges is the energy, and the second is the angular momentum. Now let us imagine the picture. Let this be the black hole, and therefore its ergo region looks like this. Notice that it touches the black hole at the poles. So let us consider the process within the ergosphere. So the external observer on a rocket, we jet some waste in the direction of a black hole. So we jet some waste with, and this is, so with some momentum which I'll call P waste and P, maybe even P jet. That's the better word. And P of, and the momentum of us. So we have the momentum conservation naturally. So we have P equals P us plus P jet. Similarly, we have the energy conservation. So the energy is however, since we are in the ergosphere, we can have, and the energy is defined with respect to stationary killing field, we can actually have negative energy. So since K mu is spaced like an ergosphere, if we, in the ergosphere, and of course the energy, and of course the momentum, so the ergosphere, and of course the momentum is a future-directed vector. We can have negative energy. So we can have and we have negative energy, which means that by the energy conservation, we have now gained some energy and momentum. This is an absolutely valid process of energy extraction. This is an absolutely valid process of energy extraction, and the energy comes from the black hole itself. This process comes at slowing down the rotation of the black hole. Of course, in real scenarios, the black holes are huge and we are tiny, so this process is This is an absolutely valid process to take. Okay. Yes, and since the black hole slows down, so similar to the rise in inertia from black hole, we cannot similar to the rise in inertia from black hole, we cannot charge it to become the extremal black hole. And similarly here, we cannot feed it with matter such that its angular momentum would increase. And it attains the extremal limit.